All right, everybody, welcome to the notes on Chapter 6, Section 4. We're going to talk about rational exponents today. A rational is just a fraction, so we're really talking about exponents that are fractions, okay? Let's take a look right here. If a to the x equals the fourth root of a cubed, then by definition, a to the x times a to the x times a to the x equals a cubed. By adding exponents, we can get a to the 4x equals a cubed, so x is 3/4. This suggests an alternative notation for radical expressions in which, for example, this equals this, okay? And this is the big thing that we're going to practice. So instead of writing the fourth root of a cubed, we could write it as a to the 3/4, okay? We could think of it as the exponent under the radical stays on top, and then the index goes on the bottom, okay? This is a square root, so that's just 36 to the 1/2. This would be 64th to the 1/3. This would be 16 to the 1/4, and so on. Okay. So sometimes we're just asked to simplify. That's no problem. We can write this 216 to the 1/3 as just the cube root of 216. So it's just 6. 7 times 1/2. 7 to the 1/2 times 7 to the 1/2 would just equal square root of 7 times square root of 7, which is just 7. So simple stuff at the beginning, just as far as simplifying those kind of problems. And then we also have one more. We have 5 to the 1/4 times 125 to the 1/4 also. And when we multiply those, we multiply inside. We get 625 to the 4th, and we can take the 4th root of 625 and get 5. Okay, so pretty simple stuff. Your calculator will do a lot of this, but it's good to understand how to do it by hand. If you could take a second and try and answer 1A, 1B, and 1C, that would be terrific. Go ahead and do that now. Pause the video and get answers to those. All right, you've unpaused. Hopefully right here you got 8. Hopefully right here you got 11. And hopefully right here you got 6. If you didn't, go ahead and pause the video, try those again. Still don't get them, make sure you see me, or make sure you make note of it, and we'll talk about it tomorrow in class. Okay. If the nth root of x equals 1 over n, it follows that the law of exponents for all real numbers like this, so x to the m to the 1/nth would equal x to the 1/nth times m, which would equal the nth root of x to the m. Okay, try not to freak out. We're going to look at examples of these and make sure that it gets cleared up. If the nth root of a is a real number and m is an integer, m over n in lowest terms, all that's true, then a to the 1/nth equals the nth root of a, and a to the m over nth equals a to the m, the nth root of a to the m. Okay, so we can write that like that, and you can put it in parentheses and do that first. It doesn't matter which we do first. Okay. Sounds complicated when we see it with all the a's and the m's and the n's and the x's and all that. When we see it with real numbers, it's not really that complicated. Okay, so let's take a look at problem 2a. So it wants to know what are x to the 3/7 and y to the negative 3.5 in radical form. So if we're going to write those out, x to the 3/7 could just be the 7th root of x cubed. So we just, the 7 becomes the index, and the 3 is the exponent for x. It's really just that simple. Negative 3.5, we need to change that. We need to change that to a fraction, so we have y to the negative 7/2. When it's negative, we put it on the other side of the radical, so this is now y over 7/2. That's the square root of y to the 7th, and then we have to rationalize the denominator. So there's some work there. You know, you could list this out as y cubed this, but then obviously, like I said, we could rationalize the denominator. This would be the preferred answer for me. What are the square root of a to the 5th and the 5th root of b cubed in exponential form? Again, the index is the denominator. Okay, the index is the denominator and the power is the numerator. So this is just b to the 3/5. This is a to the 5/2. Easy peasy. Let's take a look at got it number 2. So what are the expressions w to the negative 5/8 and w to the 0.2 in radical form? What are these expressions in exponential form? And then look at the definition of a rational exponent and explain the need for the restriction that a cannot be equal to 0 if m is negative. Okay, so see if you can explain that. Go ahead and pause the video here and try and answer those questions. All right, you've unpaused. Hopefully right here for 2a, we get, and this is kind of a complicated one, and it's rationalized, so if you don't get it, that's fine. It's the 8th root of w cubed over w. Okay. The second one should be a little bit simpler. It's just the fifth root of w. Okay, the fifth root of w. If you didn't get either of those, make sure you make note of it. We'll go over them in class. B, this is just x to the 3/4 and y to the 4/5. And we're going to talk about 2c in class because I think it requires a little bit of illustration. But really the big picture is that if m is negative, if the exponent is negative, then the variable ends up in the denominator. And if the variable is in the denominator and the constant is 0, then that is an undefinable number. So that's the big picture. I think it'll look better if I can kind of illustrate that for you. So if that didn't make sense, make sure you say something in class so we can talk about that further. Problem 3, so using rational exponents, just in a word problem, for example, Kepler's third law of orbital motion, which is used all the time, shows you can approximate the period in Earth years it takes a planet to complete one orbit of the Sun. So we would use the function p equals d to the 3/2, where d is distance, and then find out how many Earth years does it take Mars to orbit the Sun. And so we just substitute the d value that's given. And then we use a calculator, and it's really not that big of a deal, okay? Not really a hard problem. Yeah, that's it. If we wanted to find the approximate length in Earth years of each planet's year, a Venetian year, if Venus is 0.72 from the Sun, and a Jovian year, which is obviously how you say years for Jupiter, is 5.46 from the Sun. So go ahead and find those, how many years it takes, like Venus to Earth years, it takes Venus to orbit the Sun, and how many Earth years it would take Jupiter. Go ahead and pause the video and try and get answers to those. Alright, you've unpaused. Hopefully for Venus, you know that it's less because it's closer, so hopefully you got 0.61. And then Jupiter's much more, it's 12.76. Okay, 12.76 Earth years to orbit the Sun there. Alright? Let's take a look down here. So properties of rational exponents. So the same property still exists. When we multiply same bases, we add. Power to a power, we multiply. And if it's 2, AB inside parentheses to a power, then the power applies to them both. All of these are the same powers that we use for exponents all the time. So something raised to a negative moves it to the other side of the fraction, takes the reciprocal of it. A to the m over a to the n, we can subtract. And then if it's a rational inside parentheses, then the exponent applies to both. So none of these are new. These are all the same powers, or same properties for powers that we've been using since Algebra 1 that we also reviewed this year. Recall from Lesson 6.2 that we've simplified products or quotients involving radicals only when they have the same index. However, you can combine radical expressions with different indexes if you convert them to expressions with rational exponents. So what that means is that earlier we said different index means you can't do anything. What we can do with rationals is if we change this 4th root of x cubed to x to the 3/4 and this 8th root of x squared to x to the 2/8, that when we divide here, it's subtraction. So it's 3/4 minus 2/8. Well, we can reduce 2/8 to get 1/4, and then we can subtract because they have a common denominator. So rational exponents allow us to do some operations with variables or with problems that we couldn't do before. So go ahead and see if you can find what is each product or quotient in simplest form. Big deal there, simplest form. Go ahead and pause the video now. Try and get those in simplest form. All right, you have unpaused. Hopefully for here you got the 4th root of 27. Hopefully for here on problem 4 you got, or problem part B, you got the 6th root of x to the 5th. And hopefully right here for part C you got the 6th root of 16,807. Okay? If you didn't, like I said, try these again, see if you can get them, go back and look at the example, see if that helps. If you still aren't, make sure you make note of it so we can check how to do these in class. We can simplify a number with rational exponents by using the properties of exponents or by converting the expression to a radical expression. So either way. So what is each number in simplest form? 16 to the negative 2/5. We could change that to 16 to the negative 5/2. And then we could change 16 to 2 to the 4th. Multiply that out and get 2 to the negative 10th. And then that's 1 over 2 to the 10th, which is 1 over 1024. We also could just change it into a radical expression by putting that on the denominator and do it that way. Take the 5th root of 16, which is, square root of 16 to the 5th, which is just 4 to the 5th, which is this. So either way, you can do it either way, whatever works best for you. If we take a look at another one here, we have negative 32 to the 4/5. So we could do that by keeping it as a rational exponent, or we could do that by changing it to a radical. Either way, we get 16. Okay, so you kind of have to pick which way is better. I know you're going to be tempted to just put all these directly into your calculator, but I really would like for us to try and solve these by hand first so we have a better working knowledge of what is actually going on. So go ahead and pause the video here, see if you can get 5A, B, and C. Go ahead and pause the video now. All right, answers here. This is 1/8. It's another reason, by the way, I don't want you to use your calculator because your calculator a lot of times is going to give you decimals. That's 8, and this is 1 over 2,187. Okay, let's take a look here. Problem 6, we can write expressions in simplest form. So this is just we're given a mess, and we have to clean it up. That's all this is. Given a mess, and we have to clean it up. Negative 8x times the square root of xy, all to the 2/5. Or sorry, excuse me, 2/3. So I make sure I apply the 2/3 to each part of it. Recognizing that negative 8 is negative 2 cubed is going to save me a lot of work and a lot of time, because then when I do 3 times 2/3, I get the squared. Everywhere else, I'm just applying the exponent to each part. And then I'm adding exponents when the bases are the same, which is how we get 4 to the x times the cube root of y. Over here, this is negative 3/4, so 16y to the negative 8 to the negative 3/4. So I apply the exponent negative 3/4 to each term, each part of the term. So 16 to the negative 3/4 ends up being 2 to the negative 1/3, which is 1/8. Y to the negative 8 to the negative 3/4 ends up being y to the positive 6. That just stays on the numerator. Go ahead and try these. Again, we're just given a mess. We got to clean it up. Okay, try these and we'll check them. All right, the answer to A is 1 over 2x to the 5th. And the answer to B is 27x times the 8th root of x to the 4th y cubed. As always, if you didn't get those, I really think you should try them again, see if you can get them. If you still can't, make a note and we'll go over it in class. That's it for the notes this time. Do me a favor and share this link with somebody you know so that hopefully they see them, so hopefully they're prepared. Tweet it, like it, favorite it, Instagram it, make it part of your Snap story. I don't care. We need more people watching the notes. Thanks, guys. See you next time. Bye.